All right, so we're going to continue. This is kind of where we left off yesterday. Just to recap, we'll finish this today. Yesterday we talked about psychological research, and we talked about the most ideal type of psychological research, which is an experiment. All right, that's kind of where I want to start. That's my launching off point. Experimentation is the most solidified way to get a scientific finding. Yes? The quiz is Friday. The test is next Thursday, a week from tomorrow. Quiz is Friday, the test is next Thursday. The study guide is posted, so you guys can start working on that. Somebody emailed me yesterday and said they couldn't find it. Make sure you check Teams. If you can't get it on the website, because I know that app that I use on the website is not always user-friendly, so it's on Teams also. You can find it that way. So yesterday we kind of left off with this experimental design is the most ideal, right? Because we can go in a lab setting and we can control for the weather and the lighting and all the variables that we can eliminate to find cause and effect. So we created two columns. We have an experiment column and we have a correlational study column. And where we kind of left off was the difference between these two vocab words here. Random sampling versus random assignment. Right? So random sampling is a term that refers to survey data. I don't remember if I mentioned this or not, but an example of random sampling would be if you go to the cafeteria during third lunch and you give a survey to every fifth kid in line. That's random sampling. So put random sampling in your correlational column because you're randomly sampling people to participate in your survey, your study. Random assignment, though, that's an experiment word. Random assignment means, let's say 24 people agree to be in your study. Well, you randomly assign 12 to this group and 12 to that group. Group A, Group B, Group A, Group B, Group A, Group B. The example I gave was the Stanford Prison Experiment example. Randomly assign 1, 2, 1, 2, 1, 2. So then this side, you guys are going to be the guards. This side, in this experiment, you guys are going to be the inmates. Random is important. What you're going to have to know on FRQs in the future is how do we achieve random assignment? Well, you might have to physically write something like so-and-so achieved random assignment by counting every other number, pulling names out of a hat. The whole point is if it's random, hopefully it's representative, right? And the same thing is true with random sampling. If you randomly sample every fifth person to take your survey, the idea is if you get a big enough sample size, it should be representative. Every fifth person that walks by in the food court, in the mall, over a 3-hour period, you should have an equal opportunity to get females and males, an equal opportunity to get white and non-white people, older and younger, kids and teenagers, old people. We want a representative sample. So thinking like an FRQ writer here, if they told you something like a survey was conducted at Gulf Breeze High School, what is one of the design flaws? You would say, well, the problem is that the sample is not representative because the age range is not representative. Everybody at a high school is only between the ages of 14 and 18. It's not representative of America as a population. How would you fix that problem, though? In order to apply this data to future studies, it would need to be what? What's the R word? Replicated. It would need to be replicated. So they'd have to do the same study at a college. They'd have to do the same study at a bus stop. They do the same study at a fast food restaurant on a Saturday. They want to get a random sample of people because you want the sample to be representative of America as a whole. So that's the difference between random sampling and random assignment. One of them is a correlational study word. The other one is an experimental design word. And then, of course, sample size. Sample size is a common issue. And that's something you're going to have to recognize. Right? We surveyed 10 people and had a 90% correlation. Time out. Your sample size is too small. You need a bigger sample size. That's the kind of like verbiage that you'll get good at using, right? Because they're setting you up. They're going to give you a prompt, and you'll become good little psychology students and evaluate our sample size is not large enough. We need to replicate it and get more people in our study, right? So let's transition into what correlational studies really are. So a correlational method is a way to gather and plot data, and we're going to put this data on a scatter plot, right? So if we didn't write this yesterday, you need to write this down. experimental data is going to be a bar graph. All right, so you can write bar graph under experiment. And that's pretty simple. Basically, let's say you had Group A and Group B. Group A got the drug in your clinical trial. Group B got a placebo. Right, so on the x-axis you have 2 bars. And then basically you have your results on the y-axis. So let me say that again. Experimental design is always going to be a bar graph. A scatter plot, though, that's going to be for lots of data. That's correlational data as a scatter plot. Yes? That would work too. That would work too. You just need something where you can compare different groups. You can do a pie chart. You can do a line graph. You need an x and y axis, right? You need an independent and a dependent variable. In a correlational study, so let me give you some examples of when we would do correlational studies. I've been throwing out some financial advice today, right? Correlational studies are good examples, or financial data is a good example of a correlational study, right? So for instance, we want to plot some data that we can't ethically experiment on. So 10 or 15 years ago, Harvard, they did this massive longitudinal study, right? And longitudinal means they used the same people over a long period of time. And what they wanted to find out, they had a theory. And just like all scientific theories, the best way to test it would be in a lab against a controlled setting so that you could try to figure out a cause. But you can't ethically test this theory. The theory was whether or not people who were impoverished but gained a bunch of money, would they stay wealthy in the next 15 years or would they lose it all? And they tested another group of people. They said, well, what about people who had a bunch of money and then they lost it all? And the problem is, how do we put that data down on paper? We can't ethically take people's money away. We also don't have 15 years to wait and give it back to them, right? So the study that I referenced before, and I don't remember if it was this class or a different one, was this long study where they said, we're going to find the data and we're going to plot it and see what happens. And so they found people throughout all walks of life in America who had made at least $1 million and lost it to bankruptcy. And then what they did was they tracked those people 15 years later to see what happened. So they say, okay, this guy was the CEO of a company. He was worth $6 million in net worth. In 1988, he filed for bankruptcy. Let's track 15 years later and see what happened financially. And they did the same thing in reverse. How do we find people who were below the poverty line and then made a bunch of money? The lottery. So they found people who won the lottery. And after taxes, they had to clear at least $1 million. So how about people who became instant millionaires overnight? And let's track them for 15 years and see what happened. By the end of the 15-year period, almost 100% of them had gone back. People who were poor and became instant millionaires, inside of 2 decades, were poor again. And the people who had been millionaires and lost everything, inside of 2 decades, they had made their money back, which is an interesting thing. So that's a great example of correlational data for this reason. We cannot pinpoint a cause, but we can predict outcomes based on this. So if you want to star or highlight or circle or something, you need to write the word underneath your correlational column. The goal of a correlational study is to gather enough data to get a trend, here's your magic word, to predict future outcomes. We want to use it as predictive validity, to predict future outcomes. That's the reason why we do correlational studies. Why would Harvard study what made people, or whether or not people became poor again, or whether or not people became wealthy again? Because they want to predict whether or not upward mobility is based on anything other than just gaining more money. Because if you can give people money and cure their poverty, then that's the solution to the economic problems in America, right? If poor people just simply lack funds and you can give them money, that's the end of poverty everywhere. But the study found that that was not the case. So there must be some other contributing factor. That's the downside to a correlational study. It doesn't give us the cause, but it does give us data that predicts that something is going to be the case or it's not going to be the case. So if you want to do a study, the example I gave is like study hours and GPA. You have to pick 2 variables. You can't pick 5 because you only have an x and a y axis on a scatter plot. So 2 variables. So let's say Again, study hours and GPA, that's one. Let's say it's like income and happiness, right? We want to plot on one axis how much money people make in tens of thousands of dollars. So every increment on your graph, 10,000, 20,000, 30,000, 40,000, right? All the way up to whatever, $1 million. And then on the y-axis, you're going to plot some kind of score, right? Happiness is not a total, it's not an amount. So we have to somehow calculate a score. So maybe you give them a survey, and there's 5 answer choices for each question, and it's like strongly disagree to strongly agree. 0 points all the way up to 5 points, I don't know. You give them a happiness score. And if the guy who makes $1 million a year on the x-axis is all the way to the extreme, is the happiest guy in our study on the y-axis, his point is going to be up there in the corner. So I'm going to give you a hint for the test that people overcomplicate and tend to get wrong. And that word is a correlational coefficient. That's a fancy vocab word that means a dot on a scatter plot. Coefficient, you learned in math class, is an x and y value. It's a dot on a grid. In this case, a scatter plot. So the x and the y value are the two variables that we're going to quantify. I'll show you a kind of an interesting comical example here in a second. But here's what, one dot will not give us a relationship, a statistical relationship. We need lots of dots. And what we're looking for is a correlation. Do these two things correlate to one another? Do they have a relationship? Are they positively correlated? Are they negatively correlated? So here's the next hint I'm going to give you. A positive or negative correlation, okay, it's kind of interesting. Because the positive or negative, it just indicates the direction of the relationship. That's important. You need to know that. So in other words, positive 1, in terms of a correlation, means that 100% of the time, those two variables positively correlate. A negative correlation means that 100% of the time, those two variables negatively correlate. It's still 100%. So in the terms of statistics, these two numbers are equal. You say, how can they be equal? One is negative. Because it's directional. Is this a negative relationship that happens 100% of the time? Or is it a positive relationship that happens 100% of the time? Right? So negative 0.82 is 82% correlation. The negative means it's a negative correlation. That's a stronger finding than a positive 0.32. So positive 32% of the time is not a greater value than a negative 82% of the time. So that's your hint. You're looking for the highest percentage. Positive or negative does not mean anything in terms of which one of them is a higher percentage. Positive and negative in mathematical terms on a grid tells you the direction of the relationship. In other words, it's not the coefficient that's positive or negative. It's the relationship that's positive or negative. Let me show you what I mean. This is a real study that was conducted. This is one of the trials with 20 dudes in it. This is kind of funny. The theory was whether or not little man syndrome was a real thing. So they decided that the two variables that they were going to plot were the height in inches of a man and his temperament score. So they somehow devised a quantifiable test that they gave to every person that agreed to participate, and they gave it a score value. So the highest value was a 95. So the lowest value was a 25. So their y-axis, the dependent variable, is going to be increments of 5, from 25 to 95. That's the score on the test. And then in this trial, we've got 20 guys. And they just plotted their height in inches against their temperament score. So each dot on the scatter plot is going to be the two variables. So our first guy here, random guy, again, ethically speaking, we can't list his name or age or whatever. So this person is 80 inches tall, x-axis 80 inches tall, and his temperament score was 75. So if you take 80 inches tall and you go up to 75, that's where my guy would go. That's a small dot. That's where he would go. And you plot each of the other 19 dots, and you get a relationship. So if we plot them all, there he is, right? We plot all of our dots, and we get a pattern here. We get a trend. So there's a way to calculate the correlational coefficient, or a way to calculate the correlational relationship. Luckily, you don't have to do that. I mean, you do have to do that in statistics class. How many of you have taken statistics class before? So this is probably not new to you. There's this big formula that's got letters and stuff in it, and you have to calculate. But this is what we're looking for. We're looking for a relationship. We're looking for a pattern here. And the conclusion mathematically is that there is a pretty strong positive correlation between a man's height in inches and his temperament. So notice our highest value here. The guy that had the highest score on the test in this trial was one of the tallest guys. Let's say he was like 77 inches tall, and his temperament score was a 90. Our first guy here that we plotted, he had almost the highest score. His temperament was a 75. Now again, we can't point to a cause. We can't say that being taller changes the chemistry of your brain. You're up higher, and so the oxygen is better and you're happier. It's not a cause, right? There's probably something else entirely that causes your temperament to be better when you're tall. Maybe it's that people treat you better, or maybe you have more self-confidence, right? But that's the point of the study. It's not an experiment. They didn't make people shorter. They didn't genetically create tall guys in a lab. That's the point of a correlational study. That's what I don't want you to miss. This is a great way to gather data that cannot be tested in a lab, right? But we still want to know. We want to know economic things about personal finance. We want to know, right? Harvard Business School again. Harvard did this study, and they wanted to find if there were statistical trends that spanned all of the poor populations of America. So in other words, let me say it this way. They wanted to see if there were some variables that existed throughout all of the impoverished populations. And they did find some, regardless of whether it was poor farmers that were white in places like Ohio and Indiana, Kentucky, whether it was inner city people in West Baltimore, Flint, Michigan, Hispanic and Latino populations in border towns in Texas and Arizona and New Mexico. People below the poverty line, regardless of race, regardless of religion, and regardless of gender, shared a lot of commonalities. And some of the things that they found were that there were ways that you could predict whether or not someone was going to become impoverished, right? Things that they all shared in common. One of them was getting pregnant in high school, having a child in high school, right? Completing the pregnancy. Now, let's keep in mind, that's not a cause, because there are outliers in every study. So if you get pregnant in high school and you have a strong moral support system and you have a strong, let's say, financial support system, you can become an outlier. And you can make it in spite of the odds. It's not a cause. But it's interesting to note for predictive purposes that there are traits, variables in this case, that exist in all the impoverished populations, regardless of race, right? So if having a child in high school puts you at a much higher likelihood that you will become impoverished in adulthood. One of them was getting married before the age of 18. And that was probably a really niche population. That was probably like conservative religious groups in either white or rural populations, the western Ohio's or western Indiana, like small town, really conservative religious sects, or even Latino populations. There's not a strong population of people who get married before the age of 18 in America. But they share something in common. They tend to be poor. Now, getting married young does not automatically deplete your bank account or make it illegal for you to make money. That's the point we're making here. But what it does is that you can look for these traits and predict things. It's the predictive likelihood of certain traits. So this is a weird, silly example. But knowing what makes people poor, that's good predictive data. Because you could say to someone, okay, here's the deal. You're about to walk through a doorway, high school sophomore. And the data says that if you walk through this doorway, metaphorically speaking, of course, that you're 82% more likely to financially destroy the rest of your future. And you're going to spend most of your adult years financially recovering from this. And if someone was armed with that knowledge and thinking logically, do you think that they would make the same decisions? Probably not. Right? People make decisions out of carelessness and ignorance. They don't intentionally do the things that sabotage their future. So again, I want to make a couple things clear. There are outliers, but it is a human bias and flaw that we tend to compare ourselves to the outliers and not the group. And I'll give you an example. So I'll post the test scores, I'll write them on the board over there, and you'll be like, I got an 82, and you're like super jacked up about your 82, and then you look at the board and see that 3 people got A's, and now you're mad. And it's great that you have high standards for yourself, but you can't compare yourself to the outliers. If you're somebody who is struggling in the inner city to climb out of the cycle of poverty, we want people to be positive. We want to encourage them to think like an outlier. But in reality, if we're being predictive and we're going to bet a paycheck on it, the likelihood that people make it out of that cycle of poverty is not very high. So we're saying go for it, yeah, but on the inside you're looking at the data and the data doesn't lie, right? That's why predictive validity matters. Correlational studies matter. If you look at your IQ score, for instance, well, I'm the smartest person in the room because my mom always told me that I was. Actually, you're fantastically average. Like 68% of the world, you have an IQ of 100. That makes you very normal. But I'm not normal, I'm elite. Most of us are not. Most of us are fantastically average, right in the middle. Because by definition, in a bell curve, the average is the most amount of people. So the point is, I don't want you to have mediocre standards and just accept mediocrity, but I want you to understand they're outliers for a reason. They're outliers for a reason. You can't hold yourself to the standard of the outliers because predictive data doesn't lie. If you survey enough people, you get a pretty good predictive reliability, right? So if I tell you, if you do this thing, 96% of the people that do that thing, they end up dying. Would you do it? Hopefully not. If 90% of the people do that thing that you're about to do and you're going to go die, you're going to play the odds? I'll be the 5% coach. All right, do you? So again, that's the point. Or a better way to look at it is like this. Let's say you had some like rare blood disorder or something like that, and you went to this specialist, and the specialist is like, all right, so we have this treatment that's on the market, but it's very experimental, right? But it has a high success rate. If you go through this clinical trial, there's an 80% chance that you'll see remission. Sign me up, doc. Where do I sign up? Right? 80% is a good diagnosis from your doctor. 80% you'll take. Now, here's another phrase I want to teach you. 50-50 is not a high correlation. That's a coin flip. If your doctor says, okay, take these pills, you're dying. If you take the pills, there's a 50% chance you'll... Now, that's better than 0 odds, but it's a coin flip. Right? So if you're desperate, you'll take 50-50 as odds. But if you're not desperate, 50-50 is not good odds. You're not excited about the prospect of getting into your college when they tell you your chances are 50-50. That's not reassuring. So the percentage matters. Right? To go back to our other slide, the percentage matters. The higher the percentage, the more likely it is. Now let's talk about positive versus negative though. So if we're doing a correlational study and we have an X and a Y value, and we find that really the X doesn't correlate with the Y, we get this big massive spread. What we're looking for on a scatter plot is density. We're looking for a density of coefficients, because that means there's a relationship there. We're also looking for a statistical trend in one direction or another. Right? If we have a positive correlation, here's what positive correlation means. It means as the X value goes up, the Y variable also goes up. So let me give you an example if that's confusing. Let's say we want to correlate money with health. So our x-axis is going to be how much money you have as your net worth or your annual income, and your y value is going to be your health score, right? 100 being the healthiest you could be. Well, if there's a positive correlation between money and health, that means as your finances go up, then your health should also go up. It's a positive correlation. Now, to show you what it looks like, just to give you a visual, this doesn't happen very often, but a perfect positive correlation looks like this. Now, here's the problem with the perfect. This is 100% correlation. That means that X and Y go up in the exact same increment. So that means, let's say the person that studied for 0 hours got a 0 on the test. And the person that studied for 1 hour got a 10 on the test. And the guy that studied for 2 hours got a 20 on the test. Right? and the girl that studied for 10 hours got 100 on the test. There has to be an exact 100% increment for it to be a perfect correlation. It almost never happens, right? That would be like an experiment. So a perfect positive correlation would look like this. It's positive because of the direction. As the x value increases, the y value also increases. Now the difference, and you're like, wow, this is a math class. Well, in psychology, we want to know variables. So the x value might be, again, that might be your income in tens of thousands of US dollars. Your y value might be your happiness score. This might be your height in inches, and this might be your temperament score. So a perfect correlation is almost never going to happen on a test. But that's a positive correlation. As the x value increases, it also, the y value increases. So what does a negative correlation look like then? Well, as the x value increases, the y value is going to decrease, right? So in this case, our happiest guy had the least amount of money. And our guy with the most amount of money is the grumpiest. So as the x value increases, the y value actually decreases. That's the difference. So a negative correlation refers to the direction. But I don't want to confuse you. This is no correlation. Negative is not bad, and positive is not good. Positive means that they both increase. Negative means that as one increases, the other decreases. No relationship means that the x-axis doesn't affect the y-axis. The x-axis has no statistical relationship to the y-axis whatsoever. Right? So when we're plotting data, if there's no statistical relationship, one thing does not predict the other. Right? This guy is like really happy and has no money. Well, in this case, we can't predict his happiness level based on his income. There's no relationship there. Right? So there's a couple takeaways there for the test. Positive just means going up. Negative directionally means going down. Negative number, or negative and positive number, does not indicate the strength of the relationship. And you're going to have to know that on a test. They're going to give you 5 different decimal pointed numbers, 5 different ratios, and you're looking for the strongest relationship regardless of direction. The strongest relationship regardless of direction. So a correlation that is negative, but it's 82%, that's a much stronger number. I'm not going to say higher or lower. That's a much stronger number than a positive correlation that's only 32%. Right? So in other words, ignore the positive or negative. When it's asking you for the strongest statistical relationship, they want to know what is the highest percentage. Doesn't matter which direction. The highest percentage. All right. A couple things. Again, I mentioned it again. It's so important. Correlation, the purpose of a correlational study is to predict future events. Right? If we can't tell, the example I gave yesterday, if we can't tell what causes someone to become a serial killer, but we can find traits that serial killers all share, the goal is that we can hopefully what? What's the P word? Predict what might be an indicator of someone who's more likely to become a serial killer, right? Or if we can't cause people to be happier or more sad based on their income, the goal is we might be able to predict some of those traits, right? Or maybe it's more like AP Human Geography stuff. If you go to a developing first world country, a first stage 1 country, and you look at their infant mortality rates, right? Let's say your infant mortality rates is your x-axis, and your y-axis is going to be something like, I don't know, the GDP, or let's say the consumer price index. And you see countries that have higher infant mortality rates actually have lower, consumer price indexes. And that's what they found. How many of you have taken AP Human Geography or are taking it? You're going to find that when you increase, I should say this, when you decrease the mortality rate, in other words, babies live longer, well, conventional wisdom says more babies equals more people. That's not actually true. More babies equals living to adulthood, which means creating infrastructure, which means a tax-paying base, which means roads and highways and schools, libraries. It means voting populations. It means soldier-age humans who can overthrow dictators. So when babies survive to adulthood, the economy gets better because you have a working class age of people. And that's what we've learned from correlational studies, right? So when the infants survive to adulthood, they tend to fix the economic problems in their countries. When you look at, and again, it's not a cause, but when you look at the most impoverished nations in the world, they have inverse population pyramids. They're overwhelmingly one gender over another one, or one age. They're really old or they're really young. They don't have sustainable populations. And it's interesting when you look at now, a country like Italy, the coronavirus and the global response to the coronavirus because of China and Italy. Well, what's unique about Italy is in terms of their demographics. Italy is the oldest median age in the world. It's the oldest country in the world. It's not a sustainable population. Italy will go extinct, actually. That's a fact. That's a demographic fact is that the Italian ethnicity of people will become extinct in the next 50 years if they don't start replacing themselves. The replacement rate is like 2 children per person. Not per family, per person. So that's 4 kids. Most people don't have 4 kids. They're not replacing themselves. Americans are not replacing themselves. White Americans are not. So you're seeing the demographic shift. White people alone, 72% of the population, that's going down. Hispanic populations have more children. Black populations have more children, right? Eastern European and Eastern Asian populations have more children. So white Americans are decreasing in a percentage. It's not just because of intermarriage. And that's not a bad thing. I'm just saying statistically, that's what we get from correlational studies, right? Data is important, but data also can be misrepresented and skewed. So let's take a look at the problems with misrepresenting data. The first one is correlation does not equal causation, and that's important to know. And here's a good example of explaining why. Let's say that somebody has low self-esteem and depression. We plotted them on this scatter plot, and we find that there's a positive correlation. Oh, let me say this. There's a negative correlation between depression and esteem. So as your depression levels increase, your self-esteem goes down. Well, what do we do with that information? Well, we can infer that either low self-esteem causes people to be depressed, or the inverse can also be true. Depression can cause people to have low self-esteem. Or what is the more likely scenario is a third one. Something else entirely causes both low self-esteem and depression. That's why correlation is not the same thing as causation. Because unless we can get 100% correlation every time, every trial, every replication, with every population, something else has caused it. Right? Happiness and income do correlate up to a point. Right? And I'll explain it to you. So basically, based on recent studies, a correlational study was massive study, found that in America, if you have the buying power of $50,000 a year, combined or singular, one income or 2 incomes together, totaling $50,000 a year, right? And they compare those people, lower middle class, with the buying power of $100,000 a year. So you see a big jump in personal satisfaction from 50 to 100 grand. But here's something that's interesting. After $100,000, it plateaus. There's almost no increase in personal satisfaction. What we can infer is that there's a certain amount of money that will increase your quality of life. But once you reach it, it doesn't exponentially go up, if that makes sense. After $100,000 a year, you don't become that much more happy with more money. So in other words, between $100,000, even in $1 million, your buying power has increased exponentially, but your satisfaction for quality of life does not. So there's a big difference between having $50,000 a year in buying power and $100,000 a year. But there's not a big difference between $100,000 and $1 million. That's kind of crazy. And we wouldn't know that if not for correlational studies. It's not a cause, but it's still important to know, right? That there is a level where we see a huge correlation, but after that, there's really not much correlation. You have really wealthy people that are depressed or anxious or stressed because they have high income jobs. Again, maybe they make a lot of money because they're surgeons, but they have a lot of stress because they're surgeons. So it causes their quality of life and their overall satisfaction to go down. Or they work a lot. They travel a lot, so they're not at home, right? So after a certain level, money and happiness do not correlate anymore. But if you're below a certain level, they massively correlate. If you make less than $50,000 a year, your quality of life is extremely low in most American cities. And it just depends where you live. In Santa Rosa County, the poverty line is $24,000 a year. The poverty line is defined as the consumer price index. How much money it costs you to buy the basic necessities of life over the course of a year. About $24,000. So, even if you could take two $24,000 salaries together and get to $48,000, now you're in that comfortable lower middle class range where you have all of your needs met. Now you don't have a very extravagant lifestyle, but you have a financially viable lifestyle, especially compared to people in other countries. Because there's other things that data tells us, right? Here's another stat for you. If you have the buying power of $50,000 a year in America, which what that means is what $50,000 will buy you, will afford you, that puts you in the top 5% of wealth in the entire world. 5%. That means you have more stuff than 95% of the 7 billion people on this planet right now. If you have the buying power of $70,000 a year, and it doesn't matter if it's combined, two people who make $40,000 a year are in the top 1% of wealth on the planet. So when you talk about income inequality in America, it's just naive and stupid. Because almost all of America are the wealthiest people on the planet. Even if you're some of the poorest Americans that exist. Because you have basic necessities and luxuries. Now, that doesn't mean that it's not a comparative statistic. But let's be honest. If you live in a city where everybody's a millionaire and you make $1 million a year, you're poor. And you say, I'm not poor. Yes, you are. Poor is a relative term. How can I be poor if I have a Ferrari? Because he has 5 Ferraris. You're the poorest guy on the block. Poor is a relative term. Rich is a relative term. So you have to look at buying power, right? And statistics don't lie. Most of you will live most of your life in adulthood very financially secure. It doesn't mean that you won't squander money or gather some debt or make some bad financial decisions. But most of us, throughout the course of our lives, will not suffer massive amounts of financial want. It's just not going to happen. Right? You're just too middle class for that. Right? You're already doing the things that prevent you from a life of poverty. All right, I like this quote. There's liars, damn liars, and statisticians. And here's why this quote is applicable. Statistics can be interpreted in a way that makes them favorable or less favorable. Let me give you an example. Here's a good example. If we were in a political debate, say like a presidential debate, and you have this data to go on, there's a lot of ways that you can interpret this data that will prove your point or not prove your point. So now when you read statistics on the internet, especially social media, it's like you get your news from TikTok, and you have to evaluate all the information at face value. For instance, it would not be statistically inaccurate, statistically false, to say that the average household income in this town is $140,000 a year. That is statistically true. But is it really though? No. Because here's the reality. What affects that mean is the range. We have a couple extreme outliers in this town. We got the guy that owns the factory that everybody works at, apparently. So if there's one millionaire in the town, this guy makes 1.4, his net worth is 1.4. Let's say this is his average salary. He makes 1.4. That's going to bring the mean way up, right? Because again, each one of these green guys is one family. Now look at the mode and the median. The mode is $40,000 a year. That means most of the families or most of the households in this town, statistically speaking the most occurring, is a $40,000 a year salary. The middle is $60,000 a year. But the average is $140,000 a year. So this is a great example of why to plot these statistics, this is not a lie, but it's misrepresentative of the truth. If you were to use the mean, it would convey an entirely different picture. You're going to read about that and answer that on your study guide. One of the questions towards the end is talking about central tendency, and it talks about how politicians manipulate data. Well, they're not making statistics up. They're choosing which are the most favorable statistics to back up their point of view, right? If you want to make this town look really privileged and affluent, you use the mean. But if you want to be more statistically accurate, you need to use the mode. Now, when the mean, the median, and the mode are all the same number, we get a bell curve. That's the definition of a bell curve. The mean, the median, and the mode are all the same. So the most accurate way to get statistical measures is to eliminate the outliers. You take the extreme outliers, and that shrinks your range down. Here's another great example of why statistics can be problematic. Here's a vocab term for you. Illusory correlation. Illusory correlation. And that's the adjective form of the word illusion. There are things that we perceive to be true, like we said yesterday. When it comes to perception, observation is not evidence, right? It's just not. There could be illusions, right? For instance, you might think that you're much more statistically likely to be pulled over and searched if you were a teenager. And the statistics just don't back that up. It's an illusion. It's something that people assume is true. Because you drive down the road and see somebody on the side of the road and you go, there's another teenager being pulled over again. There's another man being arrested again. It's an illusory correlation. If the statistics back it up, that's different. Like, for instance, here's a good example. In this poker hand, we have a flush. And in this poker hand, we have a random series of 5 cards. So which one is least statistically likely to get in your first deal? It's a trick question. You have the same statistical odds of getting these 5 cards or these 5 cards. Now, think about that for a second. You might say, wait a minute, I play poker in my friend's garage, and I never get that hand. Well, you're comparing this specific hand to any random 5 cards. I'm talking about this specific combination of 5 cards. I'm not saying you're just as statistically likely to get this hand or any other random 5 cards. But this series of cards is no less likely than that series of cards. Here's another good example. What are the statistical odds that you flip a coin and hit heads 72 times in a row? Well, they're 50-50. Why? It's just as likely that you'll flip heads 72 times in a row as that you won't. And here's why. The quarter doesn't know that you're on a streak. The quarter doesn't discriminate based on patterns. Every time you flip a coin, what are the statistical odds that you hit heads? This is horrifying. 50%. There's 2 sides. 50% chance you hit heads. So do those odds change because you've hit heads 3 times in a row? No, they do not. The chances of you hitting heads 10 times in a row are no more or no less likely than hitting a random pattern that's not heads 10 times in a row. Compared to not, right? Or compared to, no, you're not really, because it's 50% every time you flip the coin. The odds don't change from flip to flip. Well, because here's the problem. What you're saying is very logical, but the problem is this. You are just as likely to get a tails every time as you get a heads. So it's not like the coin is breaking up the pattern, but it's an equal chance that you're going to get tails. So with a 50-50 shot every time, yeah, it's fair to say that my odds are not great that I flip it 72 times and get the same one. But that's because every single time you flip the coin, you have an equal chance of getting heads or equal chance of getting tails. So your odds don't change the 10th flip from the first flip, right? But yes, what you're saying is also true. What if I flip a coin 72 times? What are the odds that I get the same pattern the first 72 times versus the second 72 times? You're right, that's not the same. So, again, that's statistical odds. That's ratios. Now, again, back to the bell curve. We're getting close to the end here. The normal bell curve, as demonstrated in an IQ test. An IQ test is always a perfect bell curve, and here's why. The formula for calculating your intelligence quotient is based on this. You take a test. That test tells you what your mental capability is. So you take a test and you get a mental age of 17 years old. So here's the formula for IQ. It's mental age over actual chronological age times 100. You'll see that in a later chapter. You don't need to know that by heart yet. So let's say you take the test and you score what a 17-year-old mental age should be. And you're also actually 17 years old. So your mental age over your chronological age. 17 over 17 is what? 1 times 100 is 100. So 68% of the people, every single time, 68% of the people who take an IQ test will land at 100. Because in order to be higher than 100, your mental ability has to be above that mean. You say, well, how do they know what a 17-year-old can do? Because they tested 1 million of them and found out where they were. It's just like an AP exam. Our AP exam is scaled. Well, how do they know what's going to be 66% of the scores? They don't until you take the test. And then they find 66% of the scores, and they make that a 3. So in order for you to do really well on this test, it really doesn't matter how many questions you get right. It matters how many questions above the mean that you get right. You don't have to be better than the test. You have to be better than the homeboy who's taking it next to you. If the test is hard and his score is lower, that's good for you. So there's usually 2 versions of the test, and one of them sucks. So if you get the really hard version, you should be excited, because there are people that are just going to get assassinated by that test. Get like 40% of the questions right. And you get 65% of the questions right and pass. Right? In fact, one year the test was so hard, right, it really should have been invalidated, but they can. It's after the fact. This doesn't make a valid test. The test was so hard, and you see this in other AP exams, that the mean score was a 55. Well, guess what that means? 55 is a 3, ladies and gentlemen. Congratulations and welcome to the show. That's a fair and valid assessment, because the test is hard. We're comparing how much you know. Because what is a college going to do? The college is going to say, how much did you learn in this class? Did you learn enough to not have to take it again? Well, how do they know? They don't know because your nice teacher in North Carolina gave you an A. They know because you did way better than everyone else in the country who took the same test under the same conditions. It's an experiment. That's the great irony of it. It's experimental design, control group versus experiment. You got a 5 because you are in the top 20 percentile of scores. And so the Auburn is going to go, congratulations. I don't need to see anymore. Say less. Come on in, right? That's what they're going to say. Not really. That would be cool, but that's not what they're going to say. They're going to say, you don't have to take psychology in college because you're already 80% better than everybody else in the country who took it. If I created the test, it wouldn't be valid because you're not taking the same test on the same day under the same conditions. It has to be comparative. So an IQ test, people say, is unfair. Well, it's literally not, because all it's doing is assessing you compared to everybody else. The downside to an IQ test is that your IQ, in theory, goes down as you get older. That doesn't make any sense. Well, because think about this. When you're 5 and you score a mental age of 7, right, and then by the time you're 7, your mental age is not 2 years ahead anymore. Your peers have caught up to you. It doesn't mean you're any less smart. It just means the people around you are smarter, right? So the results of the test make it seem like you got dumber. You didn't get dumber. Everybody else got smarter. Yes? There are different IQ tests. So some of them are more valid than others. This one right here, the Wechsler Intelligence Scale. So the Wechsler test is probably what you take if you were in gifted. So there's a Wechsler test for children, the Wechsler Intelligence Scale for children, WISC, like Wisconsin. And that test consists of things that are not biased based on culture and language. So for instance, they'll give you shapes. And the question will say, which of the following answer choices would be if you made 1/4 turn? And you have to get the answer right. You guys remember that test? Or they give you the shape of an animal, and you have to put it together, right? So that eliminates the bias of non-native speakers and cultural references. The original IQ test that was created by a guy named Alfred Binet is a little bit culturally biased. It's very niche to Parisian French people because that's where it was created, and it was turn of the century. So, to answer your question, there are several different IQ tests. Some of them are more valid than others. If it assesses your aptitude, right, like say the ASVAB to get into the military, they're not testing your intelligence. They're testing your ability of skill sets in a cluster of skill sets. So there are different IQ tests. And if they are not a bell curve, they are not valid. All right, now here's some more vocab. You don't really necessarily need to define them now and later, but I'm going to explain to you how they're different. These are called measures of central tendency. That's what they're called. That's a vocab word. What we're looking for are trends or patterns. So just like you learned in math class, we have the mean, median, and mode. Mean is the average. You average out a score. Think about median as a literal term. When you're driving down Highway 98, the two lanes are separated by what? A median. Median means the middle. So when we say medial temporal lobe, or ventromedial prefrontal cortex, median means what? In the middle. And you'll learn the ventral side, just like dolphins, as opposed to the dorsal side is the bottom. So when we say ventromedial, it's the middle of the bottom. That's what ventromedial means. In the middle of the distribution of scores. The middle of the range, yes. That's a good way to look at it. In the middle of the range of scores. So when let's say we had 10 people take a test, we put them in numerical order, and we'd go in the middle. Find the fifth one. And you guys probably know from math class, if it's an even number, you have to average them out to get the median, right? If you have an even number, you get two middle scores. So think median as a literal term. That's the one in the middle of all the scores when they're put numerically in order. The mode, think MO, as in most. That's the most occurring score. The mode is the most occurring score, right? So if we take a test and that mean score is a 77, but 12 people got B's, the mode is a little bit higher than the mean, which means we had a low score, or a couple low scores, right? The mean changes and moves as the extremes change and move. So the range matters, right? If the high score is a 92 and the lowest score is a 62, that's a good range. You're going to get pretty close to a bell curve. But if the high score is a 98 and the low score is a 38, that's going to affect the mean. And finally, again, the purpose for statistical data is to predict. We have the range, which again is the highest to lowest. That's the actual distribution. And standard deviation. That's one that people tend to get wrong. Standard deviation means what is the average number of integers away from the mean, right? So say, for instance, like the average score is a 77, but the standard deviation is 5. Well, that means it's 5 percentage points away from a 77. The next score is 5 points higher or 5 points lower in increments of 5. It's usually not. It's usually like a 1 point something. So standard deviation, we're talking about deviating away from the mean in both directions. Right? So variation helps us understand how similar or diverse our scores are. Low variability, which is a widespread, means that there's not much of a relationship there. And greater reliability and greater predictability, right? And that is that. So does anybody have any questions about statistical data or measures of central tendency? That's a big portion of the chapter. So if you guys start working on your study guide, these are from several different modules.